Okay, so let me get started. A few years ago, when I was trying to explain part of this area of research that I'm about to share with you with some friends, one of them said, "Oh, I see. You are an apophenic." And I honestly had no idea what they meant because I didn't even know that apophenia was a word. So of course I went back and looked up what the word meant. And apparently the word apophenia or patternicity refers to a very natural and universal human tendency to see patterns in random objects, even if they don't have any special meaning. So one example of it, of course, is when you see cloud patterns in the sky, or if you look at a clover leaf and you see some stars, like this pattern of stars on them. Now, most of the time, such patterns, the ones that we observe in the natural world, they don't seem to, they are pleasing to the eyes, but maybe don't seem to mean much more. However, if you look at the engineering and applied world, you will realize that the word recognition of patterns or configurations is an oversubscribed term. It means so many things and has so many important applications in our daily lives. For example, in facial recognition, in fingerprint identification, medical imaging in the location of tumors and other pathologies inside the anomalies inside the body. Um, in terms of machine learning, so the word pattern recognition is really used quite broadly and in many, many different contexts. So first disclaimer, my talk, in these approaches, these applications that I just mentioned, they are very data oriented, algorithmic in their approach, and not at all the direction that I intend to take today. So my talk is going to be about pattern recognition in the math world, where all of our results are going to be provable facts, and therefore many of the statements that we are able to make relate to much simpler patterns than the ones that we can get by an exhaustive search through a data analysis. Okay, so that's a confession. So with that, let me get started. I'm going to try sharing my screen and see what happens. It's the moment of truth. Okay, let me start writing now. Are you able to see my whiteboard?
Yes.
Excellent. Hold on a moment while I get this adjusted. All right. So I'm about to start writing, and I'll see if this is the right size and okay, I just wrote sets and configurations part 1. Are you able to see this, everyone?
Yes.
Yes.
Very good. And is the writing big enough, or how is it showing up at your end?
Looks excellent.
Perfect.
Okay,
Yep.
great. All right, so here we go then. So today's talk is going to be based on the following question. So here's the question that I'm going to ask myself. So suppose we have a set E, and just to fix ideas, let's say this is a subset of the d-dimensional Euclidean space, or it's a discrete set in the d-dimensional set of integers. Suppose this is large. And I fully understand that this could mean many things. Then, does E contain many patterns? And I understand that from a mathematical perspective, this is an awful question to ask. I haven't described what large is, and I haven't described what patterns mean. So all of that to be unpacked slowly. However, just on the face of it, just even as an English question, one would say, yes, of course. I mean, after all, you have a whole bunch of suppose you have your set E has a ton of points like this all over the place. And just by virtue of being large and containing many patterns, of course, you can say that it contains vertices of many triangles. So here's a triangle formed by the points of E. Here is another triangle. So there are, of course, it contains many patterns, right? So now there is a line of inquiry and spearheaded by many people, including some of the prominent players in this field are Alan Greenleaf, Alex Yosevich, Crystal Taylor, Evie Paulson, Mihalis Morgoglu, Michael Bennett, so who have actually tried to quantify what many patterns in a large set means. Okay, the abundance of patterns. That's not what I'm going to talk about today, but it's important to say that there is a line of inquiry, a very vibrant line of inquiry about this out there. What I am going to talk about today, it's not just does it contain many patterns, does E contain a pattern of my choice? So does E contain a pattern P of my choice? Okay, so in case you thought that this was not very precise, this is going to get even more imprecise. So I'm going to answer this question both yes and no. Okay. Well, I'm going to answer this question in the affirmative today and in the negative tomorrow. Okay. And why? So how can the same question have two different answers, especially in mathematics? Well, so the devil is in the details. So it's really boils down to understanding what I mean by largeness and what I mean by size. Okay. So let's also unravel this question a little bit more. So when I say, does E contain a pattern P of my choice? What does this really mean? So what it means is, let's say, so fix a set P. Then does this large set E contain either, let's say, a congruent copy or perhaps an affine copy of P, i.e., does there exist a point X in RD and um, let's say T non-zero. This is for the affine bit. I'll congruent is easier. So does there exist a translation X and a dilation T such that if you look at X plus TP, that is a subset of E. Of course, this is just one rendition. You can always also throw in rotations and stuff, but I'm just going to keep things simple for now. Okay, I'm going to write down some examples of P. What kind of patterns are we interested in? So these are examples. And so here, I think you can be as imaginative as possible, although, of course, we are constrained by our available methods and what we can actually say about them. But there is no restriction on what kind of pattern you want to choose. For example, your P could be equally spaced points on a line. In other words, an arithmetic progression. On a line. So what does that mean? It means that suppose you are on some kind of a straight line and you have points that are the distance between them is exactly the same. In other words, this is an arithmetic progression. Which we will abbreviate as AP. Okay. Other examples could be, let's say, vertices of an equilateral triangle, say, or an isosceles triangle. Or let's say the vertices of a regular polygon. So that's a excuse me. So that's a geometric pattern. Okay. It could be copies of infinite sequences. Or it could be algebraic in nature. It could be solutions of equations. For example, you could look at equations of the form x plus y equal to 2z. By the way, this is a equation that depicts a three-term arithmetic progression, something that we have already talked about, or something where something truly different. Let's say 3x plus y equals 2u plus 2v. Okay. All right. So these are some examples of what patterns could be. What does large mean? So large could mean many things. non-trivial measure. So for example, you could say that if it's a finite set, and if you could use the counting measure and say that set is large if its cardinality is very large, or let's say if, for example, large counting measure, large cardinality, or a positive Lebesgue measure. It could also mean things like large dimension, a word that's very loaded, and I'm going to talk a lot about this today, or large density. Okay. So all I have done so far is to really just try and explain some of the words that show up in the first question that I posed at the beginning of my talk. Let me take a quick pause to see if there are any questions so far.
So far, so good.
Okay, excellent.
There is nothing in the chat at the moment.
Thanks, Virginia. So I'll keep moving then. Okay, so I gave you some examples of what large could mean, what patterns could mean. Maybe it's time to give you a flavor of some representative results in the subject. So let's talk about two representative results containing sets and configurations. And the first one, for the first one is in the integers, and it's a celebrated theorem due to Zemiredi. So this is a truly impactful result. And when Andrei Zemiredi was awarded the Abel Prize in recognition of his many contributions a couple of years ago, the Norwegian Academy of Sciences actually singled out this particular theorem as being the most influential of them all. So it's a result that sits at the interface of ergodic theory, number theory, combinatorics, and says the following. Suppose capital E is a subset of the natural numbers and has positive asymptotic density. Has positive asymptotic density. What does that mean? I promised you that I was going to unravel the notion of largeness, and here it comes. Positive asymptotic density means that if you look at how many points of E lie within the first capital N natural numbers, so you're looking at this set, and look at the proportion of it among the proportion of E among the first capital N natural numbers, and take the lim sup of this ratio as capital N goes to infinity. This is the asymptotic density. We assume that this is positive. And then what's the conclusion? The conclusion is for every k greater than or equal to 3, E contains a k-term arithmetic progression. So just to go back to my question, why is this a representative result answering one of the questions that I stated? Well, the reason is because this having positive asymptotic density, this is a largeness assumption. So this is a size condition that the set E is large. And if the set E is large, my question was, does it contain many patterns? And well, this K term AP is the pattern. Okay. Now for K equal to 3, this result is due to Roth. And even though Zemmeredi's theorem in full generality has multiple proofs, all of them very substantial and non-trivial, the K equal to 3 case, there are many lecture notes and textbooks available where it has been exposited in a very nice way. So for those of you who are interested in this area, may want to look up a proof of Roth's theorem. Okay. So this is Zemmeredi's theorem is a statement. This is in Z. This is in the discrete. It's in the discrete case. Let me also tell you one quick example in the continuum. And this is a classical result due to Steinhaus. And many of my colleagues here may teach this as part of an introductory measure theory course. So what does Steinhaus's theorem say? So suppose that you have, I'll just state, this is true in all RD, but let's just stick to the real line for now. So suppose E is a subset of R, and the Lebesgue measure of E is positive. Okay. Then Steinhaus's theorem says that E contains an affine copy of every finite set. Once again, this is size implies pattern type result. Having positive Lebesgue measure is a size condition and a copy of every finite set. This is the pattern P. Okay. So Steinhaus's theorem is fairly easy to prove. Once again, for the grad students in the audience, I'll leave a hint for you to sort of try this on your own. Use the Lebesgue density theorem. Okay. Now, the bulk of my talk is once I have given you an idea of what results in this area typically look like. There are many.
So can I ask you a question?
Yes, please.
So Steinhaus theory is theory in real analysis, or it looks like, is it?
Yes. Yes. So this is a result in real analysis.
Oh, I see. Okay.
So Zemmeredi's theorem is a result in combinatorics, and number theory, Steinhaus is a result in real analysis.
I mean, so that's a different level, right? So the Zemmeredi theory, I think it's a pretty high level, but
yes.
Okay.
So these two are not at the same level. However,
yeah.
Thanks for bringing this up. The next level of Steinhaus's theorem is actually a very high level, in fact, so high level that it hasn't been resolved.
Okay, so, I see.
Right. So this is it's sort of Steinhaus's theorem in terms of its proof is certainly not in the same league as Zemerides' theorem at all. But the most natural follow-up to Steinhaus's question is to ask if if E has positive Lebesgue measure, can E contain an affine copy of a given infinite set?
Okay, I see.
Okay, and
Yeah.
so there is a very old and notorious open problem here that's called the Erdős similarity problem, and the result to that very simple extension of Steinhaus's theorem is unknown. There has been many non-examples, but there is the conjecture in its fullest generality still remains open.
Okay, thank you.
Okay, all right. So let's see, any other questions?
There is nothing in the chat at the moment.
All right. So what I'm going to do then is I'm going to sort of migrate to the notion of dimension and tell you about a little bit about that. So I said that one way to measure the size of a set is through the notion of dimension. And the fact of the matter is that there is not a single notion of dimension. There are many. So I'm just going to put in a couple of definitions that are going to stay with us for the rest of this talk and tomorrow's talk. So let's see. And we are going to always assume that E is a subset of RD and it's a Borel set to avoid all sorts of other kinds of issues. So the easiest way to understand the easiest notion of dimension to understand is Minkowski dimension. So and this is probably the most visually appealing of them all. And it says that suppose that you have a set E. This is a set E, and you cover E in a fairly optimal way by epsilon balls. And suppose that you need n epsilon many is the minimum number of epsilon balls needed to cover E. And if n epsilon is roughly epsilon to the minus alpha, as epsilon goes to 0, then alpha is the Minkowski dimension. So the definition of Minkowski dimension is that the Minkowski dimension of E is the limit. Well, we can always do lim sup and lim inf and so on. So we have upper Minkowski and lower Minkowski, but I'm just not going to worry about that. So it's the log of n epsilon divided by the log of 1 over epsilon. Okay, so that's one definition. Okay, let me give you two more and then we can compare. So the second one, and this is probably one of the most heavily used notions, is the notion of Hausdorff dimension. And there are many equivalent formulations of this problem, of this concept. The one that I think may be the easiest for me to write down, usually it goes through the definition of Hausdorff measure and some kind of a cutoff threshold at which the Hausdorff measure transitions from 0 to infinity. But well, let's go for this slightly easier to state definition. So we are going to say that the Hausdorff dimension of a set E is the supremum over all exponents alpha between 0 and D, such that there exists a probability measure mu supported on E with the following property, that this mu obeys a ball condition, namely that the mass that mu allocates to a ball of radius r is always bounded above by a constant multiple of r to the alpha, no matter where you pick the ball. Okay. So this is one definition, and I'll come and talk in a little while about another equivalent definition in a moment. And even though today I won't talk about it too much, I'll just put it out there. So this is the third notion, is that of Fourier dimension. And this one goes as follows. We are going to say that the Fourier dimension of a set E is, it sort of has some superficial similarity with the Hausdorff dimension, but maybe that's not quite right. So it's the supremum over all exponents beta between 0 and d, such that there exists a probability measure mu supported on E, such that the Fourier transform of mu decays at a certain rate. In other words, the Fourier transform mu hat decays like mod xi to the power of negative beta over 2 at infinity. Okay. Now, first of all, what's the relation between all these notions of dimension, and why are there so many? Why can't we make do with less? So first of all, the good thing is that for objects that we understand that come from differential geometry, like curves and surfaces, the Hausdorff and the Minkowski dimension are completely consistent with our understanding. So curves will always have Hausdorff and Minkowski dimension 1, surfaces, surfaces will have these dimensions to be 2. But these things are trying to get at different aspects of size, and none of these three notions of dimension are necessarily, they are not the same. So some examples would help in putting things in context. So for example, there is the relation between the three, and I'll put it over here. The Hausdorff dimension, so let's say what's the relation between the two? The three, the Fourier dimension of a set E is always less than or equal to the Hausdorff dimension, and that is in turn less than or equal to the Minkowski dimension. And in general, these inequalities are strict. So for example, if you look at the dimension of the rationals, the Minkowski dimension of the rationals is 1. The Hausdorff dimension of the rationals is 0.
Malabika, can you give us a intuitive description of the Hausdorff dimension? That always sounds a mystery to students.
Yes, right. And in a moment, thank you. I will try my best. And
Okay.
in case, well, even after sort of very, very soon, I'm about to tell you why this notion of Hausdorff dimension and Fourier dimension is a mystery to me also, but I'll try my best.
Okay.
Okay. So, and for example, if you look at if E is the Cantor middle third set, then both the Hausdorff dimension and the Minkowski dimension is log 2 over log 3. Okay. So, so going back to your question, how does one motivate the definition of Hausdorff dimension as opposed to Minkowski? So the Minkowski is relatively easy to understand because after all, we do understand what covering a set by epsilon balls means. It's unclear. It's unclear just from at least from the definition that I have written down what Hausdorff dimension stands for. Well, there are alternative definitions of Hausdorff dimension that maybe points a little bit more to why this is a finer notion. And clearly this definition, this ball condition here, let me circle this, this condition you should think of as a measure of spread. So this is a measure of spread. So the more spread out or diffuse the set capital E is, it would be easier to allocate a larger value of alpha. As an extreme case, if your set E consists of a single point, then no matter what you do, the only possible probability measure that you can assign to it would be the Dirac delta, and alpha would be forced to be 0. So that's from a different point of view. The other notion, the other definition of Hausdorff dimension that I haven't written down also involves coverings, which makes it comparable with the notion of Minkowski dimension. However, this is the important fact. When you define Minkowski dimension, you always fix an epsilon, and the coverings are always going to be used using the same balls which have diameter comparable to epsilon. So you are always looking at coverings by sets of the same scale. However, for Hausdorff dimension, the notion of this notion involves coverings at many scales. So you are allowed to look at coverings at scale epsilon, epsilon over 2, epsilon over 4, epsilon times 2 to the minus j. And in some sense, you take the optimal covering over all of these combined families. This is probably one easy to state way to understand the distinction between these two dimensions. Okay.
Thank you.
You're welcome. So what I will do now is I am going to, with this, as I said, I first became interested in this line of inquiry about maybe 10, 13, 14 years ago. And there are some aspects of it where I'm still sort of scratching my head. So what I'm going to do is take a result from back then, tell you a little bit about some recent, some intermediate extensions and developments, and finish up with a very, very, very new result. It was literally posted on the archive last week, and tell you why that seems like an exciting first step. Okay. let's see. So the result that I wanted to mention, because this was my how I first got into the subject, is this result jointly with Isabella Laba. And this is from a long time ago, so probably around 2008 maybe. Okay, but let me say what this is. So suppose capital E is a subset of 0, 1, and this supports a probability measure mu obeying the following two conditions. The first one is that mu obeys a ball condition, and this should look familiar. And this is for all x in Rd, in R, and for all any radius. And number two, it has a Fourier decay condition. By the way, I omitted to tell you what the Fourier transform of mu is. I know this does not need an introduction for many of you in the audience, but just for the sake of completeness, this is what I mean. This is the Fourier transform of mu. All right. Now, mu hat of xi decays like mod xi to the power of negative beta over 2 at infinity. Okay. And this is true for some beta larger than 2/3. Okay. Then the conclusion that we managed to find was that E contains a non-trivial three-term arithmetic progression. So this was our result. And the reason I state it here is because both criteria 1 and 2 should be familiar to you in light of the definitions I put out here. Because you see, this condition number 1 is exactly the same thing that shows up in the definition of Hausdorff dimension, the ball condition. And condition 2 is the one that shows up in the definition of the Fourier dimension. So some things that we noted were that this kind of a mu exists. So, oh, I'm sorry, I forgot to put in some quantifiers without which this isn't quite right. Then for there exists an epsilon naught, and this epsilon naught is tiny and depends only on C1, C2, and beta, such that whenever alpha is larger than 1 minus epsilon naught, this E contains a non-trivial three-term maybe. Okay, so that's at least I have the quantifiers there. Okay, so going back to what I was saying, this happens, such a mu exists if the dimension of the Hausdorff dimension of E is larger than or equal to alpha. And this happens if the Fourier dimension of E is larger than or equal to beta. So one of the things that we realize, but in spite, these are not exactly the same thing. What we didn't know was that, is it possible for a set capital E, which has both large Fourier dimension and hence large Hausdorff dimension, does the same mu work for both 1 and 2? So we didn't know that. So does the same mu work? for both 1 and 2 if we simply knew that the Fourier dimension of E is large. Okay, so this was a question that was left hanging, and it was an artifact of our proof that our hypothesis needed this to happen for the same mu. At the same time, we couldn't also we found lots of examples that supported 1 and 2, and we could not find a non-example where one happened and the other didn't. Okay. Now, having said this, we had a few follow-up questions, and this has kept us busy for a long time. So some questions. Is this condition 2 really necessary? So of course, this one is sort of non-negotiable because this is related to the Hausdorff dimensionality, which is a very standard notion of size. But the question was about 2. Is 2 necessary? And can we get rid of it? And for the 3-term AP question, the answer was we were fairly convinced that we knew we had an example, and I can tell you about this example tomorrow when we start talking about avoidance problems. It is actually necessary if you are looking for the existence of 3-term APs. What I mean is that it has been well known that we know that there exists a set E, subset of 0, 1, who's with full with full Hausdorff dimension. Such that E avoids all progressions, all non-trivial. So this was known. But then over the years, jointly with Vincent Chan, Kevin Oreo, and others, we have started looking at other patterns, and then it wasn't clear to what extent this was necessary. So a few years ago, in 2019, around 2019, jointly with Rob Fraser and Xiaoming Guo, what we proved was a Sarkozy type theorem of a similar flavor. So same hypothesis. So same hypothesis on mu as above. And what we were able to show is that for sufficiently large alpha, we showed that the conclusion was that E contains that there exists an X in R and a T non-zero such that E contains a polynomial pattern. So what is capital P? Well, capital P from R to R is a polynomial of degree D greater than or equal to 2, and for normalization purposes, P0 is 0. So we proved a result like this, and we weren't sure, at least I wasn't sure at the time, is 2 necessary for that? Is 2 needed? Okay. And we could not find a counterexample, an example where that showed that similar to this one, the counterexample above, which would show the necessity of this condition. Okay, So maybe I should tell you where in the proof um, conditions like 1 and 2 show up, and that will give you maybe a better appreciation of where what kind of role these two criteria play in the proofs. And this is important in its own right. So where do we need to? So where is 2 needed? So this is a word about so one of the first things that we do when we are trying to locate patterns is to create a multilinear form that quantifies the pattern. So what we are looking for is a multilinear form, and I'll write down it what a multilinear form looks like for the easiest case, which is for 3-term APs. Okay. So I'll first do it for, so let's say we are looking at this integral, and let's call this lambda of f. We are going to look at d mu x, d mu y, d mu x plus y, or maybe I should say, because otherwise we'll have to say x plus y over 2. Okay, and there should be an f somewhere. So let's say we are integrating this against f of xy. Okay. You see, right now, I haven't said anything about whether is this meaningful. So what exactly does this mean? Just because I wrote down a bunch of integrals doesn't mean that it converges. But something to sort of note is that if mu was an absolutely continuous measure, and if lambda was non-zero, that would signal the presence of 3-term APs in the support of mu. So one of the first things that we do for a singular measure is to identify this as, say that lambda can be identified with a non-negative measure supported on the set of xy in E cross E such that x plus y over 2 is also in E. So this requires a proof, and this was one of our main results. One way to make sense of this is to notice, let's just say f is identically 1. If you rewrite everything in terms of the Fourier transform, one of the things that you will notice is that this can be rewritten in this way, and I'll spare you the details. And this integral is convergent provided mu hat is in L3. And condition 2 implies this property, which leads to the making sense of lambda of f. Okay. What we have been sort of trying to understand since then is how, to what extent is 2 necessary for more general polynomial patterns. And I want to end with a very interesting, very recent post which appeared on the archive on October 28th. So this is brand new. And due to, by the way, maybe I should stop and check with Virginia. Virginia, when would you like me to stop? Do I have maybe 3 more minutes?
You do have 3 more minutes, yes.
Perfect. So this is just enough time. So this is the work of 3 people: Boris Kuka, Tuomas Arponen, and Tuomas Salston, who proved the following. So they pick a very special P, but in our class, so P is the square T square, and they show, and they drop the condition 2 entirely. So they show that there exists an absolute small constant epsilon naught such that if the Hausdorff dimension of E is larger than 2 minus epsilon naught, then E contains x, x plus t square for some choice of x and some t non-zero. And the reason this is exciting is that apart from dropping the condition 2, what it tries to do is it goes back to these it goes back to the Fourier decay condition that we had, and it shows that it's of course not 2 is not necessary, but they do say that some kind of having smallness of the Fourier transform is important. And then they go about proving that they construct a measure which has this smallness property. So main idea of the proof is the construction of a measure mu on E with what they call a spectral gap, and I will say in a moment what that is. So what is a spectral gap? It's one where it has this property that mu hat xi square in a certain interval is really, really small. And also on the other side, the energy of the measure is finite, is some constant. This is not anything new, because there is an alternative definition of the Hausdorff dimension involving finiteness of the energy. And then they show that the spectral gap condition implies the existence of this polynomial pattern. And the reason I find it, maybe I should end by saying why I find this exciting, is because you see, there are many harmonic analysis problems where curvature plays an important role. Curvature leads to Fourier decay, and there are many examples in restriction theory where the curvature enters in a really fundamental way to prove non-trivial theorems. In this fractal regime, in the regime of sets and configurations, arithmetic progressions, these are patterns that lie on a line, and we now have ample proof why, without Fourier decay of some kind, it is not possible to identify such patterns. And yet, this new work of Kuka, Orponen, and Solsten show that if the pattern itself comes from a polynomial of degree larger than or equal to 2, a pattern that has curvature, the Fourier decay assumption can be dispensed with. In other words, there is some kind of an interplay between the Fourier decay of the supporting set and the Fourier decay of the set on which the pattern lies. And this is an area which I think has immense potential, and I hope this will keep us busy for some time to come. Thank you for your attention.